So in section 18.3, we're going to look at reactions that involve the hydride ion. And so you can see here there's some reagents here that provide hydrides, lithium aluminum hydride, sodium borohydride, and sodium hydride. Now, I want to remind you that when we talk about a hydride, it's a hydrogen with 2 electrons and a negative charge, okay? Now, you'll see it a lot of times abbreviated like this. Now, when we think of things with negative charges, a lot of times chlorine and the hydroxide ion pop into view, and so it may be tempting to draw some similarities there. However, unlike chlorine minus or OH minus, a hydride ion, H minus, doesn't exist on its own because in any amount in a concentration and solution, because it's so reactive, both as a nucleophile and a base. It even reacts with a lot of really common solvents that are unreactive with most other things. So, of course, the question, is why? Why is this so reactive? It's so reactive because it's really small in size, right? And its nucleus is only moderately electronegative, so it doesn't accommodate that negative charge very well. Okay. Now, if this looks familiar to you, we saw lithium aluminum hydride and sodium borohydride in chapter 7. And I just want to remind you, in both of these cases, the hydrogen there is covalently bonded to a less electronegative atom, either the boron or the aluminum. So hydrogen here has a partial negative charge. In many instances, what we do in organic chemistry is instead of writing these out, we simply think of sodium borohydride and lithium aluminum hydride as H minus. And I'm going to show you this in some of the mechanisms, but that's an assumption that we make, and it's pretty common. So let's look at some of the reactions with nonpolar pi bonds that we see. What we see here is butane 2-one, right, being treated with an aqueous solution of sodium borohydride. When that occurs, we now form an alcohol, and that's butane 2-ol. And this is a racemic mixture because notice we've got a new tetrahedral center here, and this has 4 different groups. Okay, so always check to make sure that we've got 4 different groups if we've got a racemic mixture. So we can use this now to form an alcohol. I want you to notice too with lithium aluminum hydride, we can kind of do this same reaction and form the same product here. In general, right, sodium borohydride or lithium aluminum hydride can be used to convert a ketone to a secondary alcohol. Okay, and we can see this in both of these cases here. Now, it can also, sodium borohydride or lithium aluminum hydride can also be used to convert an aldehyde to a primary alcohol. You can see 2 examples here where benzaldehyde is converted to phenylmethanol. And so now we're forming a primary alcohol. Let's look at these mechanisms for just a moment. When we look at this mechanism, it says it's a simplified mechanism, and I'm going to show you why once I draw my ketone. So there's our ketone. We are simplifying this by just using a hydride. Okay, So there's the hydride. Hydride is nucleophilic. I want us to remember that this oxygen is very electronegative. It's going to withdraw electron density. That carbon is partially positive. So these electrons are going to go right here and attack that partially positive carbon. Those electrons are going to jump up there on the oxygen. Now, we have formed a new bond with that hydride right there. And now this is our oxygen here. We're going to go through a second step, which is a proton transfer. And so what you're going to see here, this would be like an acid workup step. Where these electrons are going to come out, they're going to grab a proton. Those electrons are going to go back on the oxygen. Forgot to write down this was a nucleophilic addition step. Right, and now we have our alcohol. I did not show the hydrogen there because remember, not all stick structures show a hydrogen, so I just went ahead and left that off. If you want to show the hydrogen, that's completely fine. I just didn't do that. So that's a simplified mechanism of sodium borohydride with a ketone. I also want us to look at a simplified mechanism with an aldehyde as well as lithium aluminum hydride. So let's do that here. This is from one of the previous equations. Right. So here's our hydride. Sorry, here's our ketone. Here is our hydride. It's going to come up here and attack that carbon because that's partially positive. Those electrons are going to go up on that oxygen. It goes through its normal nucleophilic addition. Oh, no, I got excited and did not write that correctly, so hold on. Where the hydride has added there, it's again going to go through a proton transfer. Where these electrons are going to come and grab that proton. Those electrons are going to go back there to form water. And again, I'm not going to show that hydrogen. You can if you want. It's still there. We just don't have to show it. And so now we have our primary alcohol. Because the hydride can't exist on its own, if we were going to show a more complete, detailed mechanism, we would have to show the nucleophilic attack as a hydride transfer. So when we talk about this, and you can show the simplified mechanism, but I do want you to kind of see what's going on. So if we have BH, so sodium borohydride, the sodium's a spectator ion, so that's gone. There's BH3. We would show this as a hydride transfer, where the arrow starts here from the middle of that bond, attacking down here, and those electrons go there. Okay? And those electrons go whoop, right up here. Sorry, I drew my arrow too short. And so we get this intermediate It looks like that, and those electrons go there. And then again, we're going to get another hydride transfer down there. Right, and there we go. It is okay if I ask for the mechanism for you to show the simplified one, okay? But I did want you to see this in case you ever run into this anywhere else. Now, nucleophilic addition of sodium borohydride to a ketone or an aldehyde generally takes place in solvents like water and alcohol. That's super advantageous because those solvents are weak acids. So the addition of H- to the carbonyl group and then the protonation can occur in that same synthetic step. But nucleophilic additions that involve lithium aluminum hydride can't take place in water or alcohol because the lithium aluminum hydride is just too reactive. The hydride from the lithium aluminum hydride deprotonates the kind of weakly acidic proton from the water or the alcohol very quickly, producing hydrogen gas that is very flammable. This is also a very exothermic reaction. So it can ignite and cause an explosion. So we tend to not use those as our solvents. So that's why it gets a separate acid workup step. Although sodium borohydride can deprotonate water and alcohol, it is super, super slow, especially when the solution's maintained in a slightly basic pH. So it's just really too slow to be a concern. Now, I'm sure the burning question in your heart is, why is lithium aluminum hydride more reactive than sodium borohydride? Okay, well, lithium aluminum hydride is more reactive than sodium borohydride because the electronegativity difference. So the electronegativity of aluminum is 1.16, and that's a lot lower than boron, which is 2.04. And both, of course, are lower than hydrogen, which is 2.20. Because of this, hydrogen is a partially negative charge with both of these, either the aluminum hydride or the boron hydride. But the electronegativity difference is greater in the case of aluminum, bigger electronegativity difference. And so that means there's a higher concentration of negative charge in lithium aluminum hydride than sodium borohydride. And as we learned, a higher concentration of charge, right here, a higher concentration of charge makes lithium aluminum hydride less stable, right? And if something's less stable, it's more reactive, okay? And so that's something that we see, and the reason that lithium aluminum hydride is so much more reactive. Now, as I mentioned in the previous screencast, compound classes with polar pi bonds other than carbonyl groups react with can react in similar ways. Specifically, if you have an imine, which is a carbon double bonded to a nitrogen. And so what we see here is that these react in much the same way to a carbonyl. They go on and produce amines, right? If we start with a double bond, this is a reduction reaction. So you're going to see, like, for example, the words an imine is reduced with sodium borohydride or lithium aluminum hydride. And over here, we're forming an amine. So we're changing our functional groups. Now, I want you to notice that, just as I mentioned earlier, we can use methanol as a solvent there, but we are not using it as a solvent with lithium aluminum hydride. It's too reactive. Now, I'm sure the burning question of your heart is, hey, Dr. Pierce, if imines can react, can nitriles be reduced? And the answer to that is yes. A nitrile can also be reduced by lithium aluminum hydride. So if we have a nitrile here, There's the first addition of a hydride, results in a charged intermediate with a carbon nitrogen double bond, which then is going to go through a second addition of a hydride, right? And this resembles, this dianion here kind of resembles the nitrogen atom. Well, it's the nitrogen atom, right? And when you do an acid workup on the nitrogen atom, it gets protonated twice until we end up with a primary amine here. So this is a nice way to take a nitrile functional group and convert it to a primary amine functional group. Now, at the very beginning of this, I mentioned sodium borohydride, lithium aluminum hydride, but I also mentioned sodium hydride, which is another common hydride agent used in organic chemistry. It's a super powerful base, so it's often a really good choice for reactions that require the deprotonation of a weakly acidic proton, similar to like what we would see in the Williamson ether synthesis or the alpha alkylation of a ketone or aldehyde. Now, even though sodium hydride is a good source of hydride, it does behave differently than sodium borohydride or lithium aluminum hydride. And what we mean by that is that sodium hydride is a very strong base, but a poor nucleophile. Now, so remember, sodium borohydride and lithium aluminum hydride were good, strong bases and also strong nucleophiles, right? Well, here we have a poor nucleophile. So sodium borohydride and lithium aluminum hydride would, for example, favor the addition of a hydride to a carbonyl group of a ketone or aldehyde. Sodium hydride, on the other hand, will favor deprotonation to yield an enolate ion right here quantitatively. And what that means is that's about 100% yield, which is shown right here. So instead of reacting here, it's going to deprotonate the one of these acidic hydrogens, okay? Sodium hydride behaves differently because it is an ionic hydride. Lithium aluminum hydride and sodium borohydride are covalent hydrides. Okay. And so because these are covalent, it just means they don't quite have a big of a difference in electronegativity as an ionic bond. So there's a really big difference here in electronegativity, and it's classified as an ionic bond. So because it's ionic, it's basically insoluble in organic solvents. It remains a solid. So it's believed that these reactions involving sodium hydride take place at the sodium hydride surface. And so that means the hydride then directly participates in the reaction. So it could conceivably act as a base or nucleophile. However, studies have shown that it generally only acts as a base because proton transfers are so very fast. And so that's kind of what we see there. Now, let's go through and do a problem where we can show the mechanism for this. So here's a problem. It says, predict the major product of the reaction shown here. When we look at a problem like this, we're going to look at what our substrate is, and we're going to look at it and say, okay, what functional group does it have? It's got an aldehyde functional group. So over here we have an aldehyde. And then we say, okay, look, we've got sodium hydride and then CH3I, which is an alkyl halide. And so we need to think about the types of reactions we can do. We're going to put these in order. And so then we need to ask ourselves, will the hydride anion from sodium hydride attack as a base or as a nucleophile? So as we just mentioned, sodium hydride is a strong base, right? But a poor nucleophile. So instead, it will deprotonate at the acidic site. Okay, and so when it deprotonates at the acidic site, when we think about this molecule, okay, there's a hydrogen, there's the double bond. We have here, right, two hydrogens that are acidic, okay? And so when we look at this, okay, and we have an aldehyde, I want to remind you, because this was way back in chapter 10, the aldehyde hydrogen here is not acidic at all, but the alpha carbon, and the alpha carbon is one carbon away from the carbonyl site, is acidic, and so these two here are acidic hydrogens. So what that means then is that when we have a hydride that comes in and reacts, it reacts as a base, and we know acids and bases react together. That's an acidic hydrogen. It will attack there, and these electrons will go on the carbon. Now, when it does that, we now have a negative bond, or a negative atom here. Not a negative bond, a negative atom, right? And so we've done the first reaction, so now we have to go to number 2. And we say, okay, let's think back. What happens when I have an alkyl halide? Well, when I have an alkyl halide, I know that's super electronegative. It's going to withdraw electron density. That's a halogen. That's going to make this partially positive. Well, over here, I have this negative charge, and I know that we're going to go from something that's negative to positive. So this can undergo an SN2 reaction, where these electrons come right here, attack that carbon, and those electrons go on the iodine. And you end up with no. Sorry. A CH3 there, and 9 minus there, right? And so I want you to point out that this is going to be a racemic mixture because we have 4 groups that are attached, and they're different groups, and so we can end up with a racemic mixture. So this concludes section 18.3. In the next section, we're going to look at reactions of organometallic compounds, specifically alkyl lithium reagents and Grignard reagents.